A light-emitting diode is a two-lead semiconductor light source. It is a PN junction diode, which emits light when activated. When a suitable voltage is applied to the leads, electrons are able to recombine with electron holes within the device, releasing energy in the form of photons. This effect is called electroluminescence, and the color of the light is determined by the energy band gap of the semiconductor, and lead is often small in area, and integrated optical components may be used to shape its radiation pattern. Appearing as practical electronic components in 1962, the earliest LEDs emitted low-intensity infrared light. Infrared LEDs are still frequently used as transmitting elements in remote control circuits, such as those in remote controls for a wide variety of consumer electronics. The first visible light LEDs were also of low intensity, and limited to red. Modern LEDs are available across the visible, ultraviolet, and infrared wavelengths, with very high brightness. Early LEDs were often used as indicator lamps for electronic devices, replacing small incandescent bulbs. They were soon packaged into numeric readouts in the form of 7-segment displays, and were commonly seen in digital clocks. Recent developments in LEDs permit them to be used in environmental and task lighting. LEDs have many advantages over incandescent light sources, including lower energy consumption, longer lifetime, improved physical robustness, smaller size, and faster switching. Light-emitting diodes are now used in applications as diverse as aviation lighting, automotive headlamps, advertising, general lighting, traffic signals, camera flashes, and lighted wallpaper. As of 2015 update, LEDs powerful enough for room lighting remain somewhat more expensive, and require more precise current and heat management than compact fluorescent lamp sources of comparable output. LEDs have allowed new text video displays and sensors to be developed, while their high switching rates are also used in advanced communications technology. History, discoveries, and early devices. Electroluminescence as a phenomenon was discovered in 1907 by the British experimenter H.J. Round of Marconi Labs, using a crystal of silicon carbide and a cat's whisker detector. Soviet inventor Oleg Losov reported creation of the first LED in 1927. His research was distributed in Soviet, German, and British scientific journals, but no practical use was made of the discovery for several decades. Kurt Lehovec, Carl Ricardo, and Edward Jamgochin explained these first light-emitting diodes in 1951 using an apparatus employing SiC crystals with a current source of battery or pulse generator, and with a comparison to a variant, pure crystal in 1953. Reuben Brownstein of the Radio Corporation of America reported on infrared emission from gallium arsenide and other semiconductor alloys in 1955. Brownstein observed infrared emission generated by simple diode structures using gallium antimonide, GaAs, indium phosphide, and silicon germanium alloys at room temperature and at 77 kelvins. In 1957, Brownstein further demonstrated that the rudimentary devices could be used for non-radio communication across a short distance. As noted by Kromer, Brownstein had set up a simple optical communications link. Music emerging from a record player was used via suitable electronics to modulate the forward current of a GaAs diode. The emitted light was detected by a PBS diode some distance away. This signal was fed into an audio amplifier, and played back by a loudspeaker. Intercepting the beam stopped the music. We had a great deal of fun playing with this setup. This setup presaged the use of LEDs for optical communication applications. In October 1961, while working at Texas Instruments in Dallas, Texas, James R. Beard and Gary Pittman discovered infrared light emission from a tunnel diode they had constructed on a GaAs substrate. Later that month, they were able to demonstrate efficient light emission and signal coupling between a GaAs PN junction light emitter and an electrically isolated semiconductor photodetector. On August 8, 1962, Beard and Pittman filed a patent titled Semiconductor Radiant Diode, based on their findings, which described a zinc-diffused p-n junction LED with a spaced cathode contact to allow for efficient emission of infrared light under forward bias. After establishing the priority of their work based on engineering notebooks predating submissions from GE Labs, RCA Research Labs, IBM Research Labs, Bell Labs, and Lincoln Lab at MIT, the U.S. Patent Office issued the two inventors the patent for the GARS infrared light-emitting diode, the first practical LED. Immediately after filing the patent, Texas Instruments began a project to manufacture infrared diodes. In October 1962, they announced the first LED commercial product, which employed a pure GARS crystal to emit a 900 nanometers light output. The first visible spectrum LED was developed in 1962 by Nick Holonyak, Jr., while working at General Electric Company. Holonyak first reported his LED in the journal Applied Physics Letters on December 1, 1962. George Crawford, a former graduate student of Holonyak, invented the first yellow LED and improved the brightness of red and red-orange LEDs by a factor of 10 in 1972. In 1976, P. Pearsall created the first high-brightness, high-efficiency LEDs for optical fiber telecommunications by inventing new semiconductor materials specifically adapted to optical fiber transmission wavelengths. Initial commercial development. The first commercial LEDs were commonly used as replacements for incandescent and neon indicator lamps, and in 7-segment displays, first inexpensive equipment such as laboratory and electronics test equipment, then later in such appliances as TVs, radios, telephones, calculators, as well as watches. Until 1968, visible and infrared LEDs were extremely costly, in the order of $200 per unit, and so had little practical use. The Monsanto Company was the first organization to mass-produce visible LEDs, using gallium arsenide phosphide in 1968 to produce red LEDs suitable for indicators. Hewlett-Packard introduced LEDs in 1968, initially using GARS supplied by Monsanto. These red LEDs were bright enough only for use as indicators, as the light output was not enough to illuminate an area. Readouts in calculators were so small that plastic lenses were built over each digit to make them legible. Later, other colors became widely available and appeared in appliances and equipment. In the 1970s, commercially successful LED devices at less than 5 cents each were produced by Fairchild Optoelectronics. These devices employed compound semiconductor chips fabricated with the planar process invented by Dr. John Hohney at Fairchild Semiconductor. The combination of planar processing for chip fabrication and innovative packaging methods enabled the team at Fairchild, led by Optoelectronics pioneer Thomas Brand, to achieve the needed cost reductions. These methods continue to be used by lead producers. Most LEDs were made in the very common 5mm T1 3/4 and 3mm T1 packages, but with rising power output, it has grown increasingly necessary to shed excess heat to maintain reliability. So more complex packages have been adapted for efficient heat dissipation. Packages for state-of-the-art high-power LEDs bear little resemblance to early LEDs. Blue LEDs were first developed by RCA in 1972. SiC types were first commercially sold in the United States by Cree in 1989. However, neither of these initial blue LEDs were very bright. The first high-brightness blue LED was demonstrated by Shuji Nakamura of Nichia Corporation in 1994 and was based on InGaN. In parallel, Izumu Akasaki and Hiroshi Amano in Nagoya were working on developing the important GaN nucleation on sapphire substrates and the demonstration of p-type doping of GaN. Nakamura, Akasaki and Amano were awarded the 2014 Nobel Prize in Physics for their work. In 1995, Alberto Barbieri at the Cardiff University Laboratory investigated the efficiency and reliability of high-brightness LEDs and demonstrated a transparent contact LED using indium tin oxide on. In 2001 and 2002, processes for growing gallium nitride LEDs on silicon were successfully demonstrated. In January 2012, Osram demonstrated high-powering GaN LEDs grown on silicon substrates commercially. White LEDs and the illumination breakthrough. The attainment of high efficiency in blue LEDs was quickly followed by the development of the first white LED. In this device, AY3Al5012 CE phosphor coating on the emitter absorbs some of the blue emission and produces yellow light through fluorescence. The combination of that yellow with remaining blue light appears white to the eye. However, using different phosphors, it also became possible to instead produce green and red light through fluorescence. The resulting mixture of red, green and blue is not only perceived by humans as white light but is superior for illumination in terms of color rendering. Whereas one cannot appreciate the color of red or green objects illuminated only by the yellow wavelengths from the YAG phosphor. The first white LEDs were expensive and inefficient. However, the light output of LEDs has increased exponentially, with a doubling occurring approximately every 36 months since the 1960s. This trend is generally attributed to the parallel development of other semiconductor technologies and advances in optics and materials science, and has been called Heitz's law after Dr. Roland Heitz. The light output and efficiency of blue and near-ultraviolet LEDs rose as the cost of reliable devices fell. This led to the use of high-power white light LEDs for the purpose of illumination, which are replacing incandescent and fluorescent lighting. White LEDs can now produce over 300 lumens per watt of electricity, while lasting up to 100,000 hours, compared to incandescent bulbs. This amounts not only to a huge increase in electrical efficiency, but a similar or better, prorated cost for the bulb's working principle. A PN junction can convert absorbed light energy into a proportional electric current. The same process is reversed here. This phenomenon is generally called electroluminescence, which can be defined as the emission of light from a semiconductor under the influence of an electric field. The charge carriers recombine in a forward-bias PN junction as the electrons cross from the N region and recombine with the holes existing in the P region. Free electrons are in the conduction band of energy levels, while holes are in the valence energy band. Thus, the energy level of the holes will be lesser than the energy levels of the electrons. Some portion of the energy must be dissipated in order to recombine the electrons and the holes. This energy is emitted in the form of heat and light. The electrons dissipate energy in the form of heat for silicon and germanium diodes, but in gallium arsenide phosphide and gallium phosphide semiconductors, the electrons dissipate energy by emitting photons. If the semiconductor is translucent, the junction becomes the source of light as it is emitted, thus becoming a light-emitting diode. But where the junction is reverse biased, no light will be produced by the LED and, on the contrary, the device may also be damaged.